Alright, go ahead and get started. So to determine the heat gained or lost during a single phase, we use this top formula. And to determine the heat gained or lost during a phase change, we use one of these formulas, depending on which phase it is. So for example, how much heat is required to melt 30 grams of ice? Will someone close the door? When you're melting ice, what you're doing is you're going between 0 degrees Celsius solid to 0 degrees Celsius liquid. So you're going between a solid to a liquid. That's what melting means. And melting occurs at the melting point, which for water it is 0 degrees. So the heat of fusion of water, or H2O, is 333 joules per gram. So the total heat during this be equal to the mass times HF. Mass is 30 grams. HF for ice is 333 joules per gram. Grams cancel out, leaving us with just joules. And we get 9,990 joules of energy. So when you're doing a phase change, you'll use one of these equations. You use heat of fusion value if it's melting or freezing, and it'll be positive for melting, and it'll be negative for freezing. How much heat is needed to raise the temperature of water by 10 degrees Celsius? So this is our change in temperature. We're increasing by 10 degrees Celsius. I could have worded this, for example, going from 20 degrees Celsius to 30 degrees Celsius. The change in temperature is 10. And let's assume that it's still 30 grams. So here we have a change in temperature. So we use the formula that has a change in temperature in it. For liquid water, 4.184 joules per gram degree Celsius is the specific heat. So 30 grams, delta C is 10 degrees Celsius. Specific heat of water is 4.184 joules for every gram to 10 degrees Celsius. So if there is no phase change, we use this formula. If there is a phase change, we use this formula. So this entire formula is used during the liquid phase only. With CP being 4.184. If we had a solid phase only, we would have to change our CP value. That's the only difference. The equation stays the same. We just have a different CP value. Everyone good? So how much energy or how much heat is needed to increase 50 grams of water or of negative 20 degrees Celsius ice to 40 degrees Celsius water. So let's think about all the changes that are going to go on. So we're going to begin with negative 20 degrees Celsius ice. And we're going to warm it up until the melting point, 0 degrees Celsius ice. Then we're going to melt and it'll become 0 degrees Celsius water. There, we will warm it up to 40 degrees Celsius water. So here, between here and here, it's a solid. Between here and here is a liquid. And between here and here is a phase change. So we're going to end up with 3 equations. I like using this little grid to help me track. So I'm starting out at negative 20 degrees Celsius. And I'm going up to 0 degrees Celsius. And eventually 40 degrees Celsius. Here is a solid. Here is a liquid. And then this is the phase change. when it melts. So during the single phase solid, so when we go from negative 20 degrees Celsius ice to 0 degrees Celsius ice, we will use this equation because we are a solid. So this is for solid only. For solid, Cp is equal to let's see if I can find it again. We'll use that the Cp for solid H2O is 2.02 joules per gram degree Celsius. 2.02. Again, I said multiple times. No, I said multiple times these numbers fluctuate so much that, again, I will always give you the formula sheet. I'll always give you a table. For example, here's sideways. Here's one table to tell you the HF, the HV values, and CP values for different things. Every single time it's going to change because some of them use like tap water, some of them use pure water, some of them use ocean water. Some of them do it up in Colorado, some of them do it at sea level. Some of them do it with temperatures around 70 degrees. Some of it do it around temperatures around 90 degrees. Some does the complete average between 0 and 100 and just the statistical average. Some of them do lower. It just fluctuates too much to have a good value. Just use whatever I tell you. Wherever the homework or test was going to have, just look at the table and put. So this is always going to be found in a table. Technically, in a lab, when you're doing this, what you would do is you'd calculate this value for whatever substance you're dealing with. So if you have certain water, maybe you're using water bottle water or not tap water, you would need to calculate this before you do any calculations. The only number I would memorize is 4.184. That's the value I'm always going to use for liquid water. But again, somewhere, you see in some tables, so for example, Like the homework I actually have for this class uses 2.01, and then I think the test uses 2.02. And then IPC, they use kilogram. IPC uses kilograms, so it'll be about 1,000. Bless you. But they have water as 4.4186. They have ice as 2093, so 2.093. And they have steam as 2009. And I don't like the fact it fluctuates too much. It's just very inconsistent. And I haven't went into the lab and calculated a precise enough value as it fluctuates too much even there. It's based on so if you're going between 0 and 10 degrees versus 90 and 100 degrees water, the value is slightly different in those two ranges. That's the reason why you don't get a good value for it. It depends on whether or not we're going from negative 10 to 0, or if we're going from negative 50 to negative 40. This value changes too much based on it. And we treat it as a constant, even though it's not really a constant. So our mass is 50 grams. Our change in temperature, we're increasing by positive 20 degrees. So negative 20 plus 20 is 0, or 0 minus negative 20. And a CP we'll use in this problem, 2.02. Just joules. So this handles this case, to where we're increasing the temperature and going up. Now we have to handle the phase change. During the phase change, we're going from 0 degrees Celsius ice, which is a solid, to 0 degrees Celsius water, which is a liquid. So the heat of fusion, so we use heat of fusion equation. And we'll use 333. And again, this we'll use 334 actually. And this is joules per gram. Again, it fluctuates too much. Just use whatever value that's associated. You just look this up. What I'm trying to get is, don't memorize these numbers. Just look it up in the table. So 50 grams times 334 joules per gram. Grams cancel out, leaving us just joules. And that'd be 16,700 joules. Then, so that covers this phase. The next thing is increasing the temperature while it's a liquid. So going from 0 degrees Celsius water to 40 degrees Celsius water. So this is a purely liquid phase. And we will use a CP value of 4.184 joule per gram degree Celsius. So Q is equal to mass times change in temperature times CP. Mass is 50 grams. Going from 0 to 40 is increasing by 40 degrees Celsius. CP 4.184 joules per gram degrees Celsius. We're going to get 8,368 joules. So the total heat would be the sum of all this. So that'd be 2020 joules plus 16,700 joules plus 8,368 joules. And that gives us a total of 27,088 joules. Everyone good? So the CP of lead is 0.128. See how much that differs from the formula here. Nope, that's exactly right for lead here. So here's the CP for lead, here's the CP for water. Suppose we dropped a 50-gram lead cube that's at 200 degrees Celsius into 500 grams of water that's at 20 degrees Celsius. Assuming no heat is lost, what is the final temperature after they reach equilibrium? Suppose we drop the 50-gram lead cube that's at 200 degrees Celsius into a 500 grams of water. By the way, 500 grams of water is how much water is in a normal water bottle. That's at 20 degrees, so about room temperature. Assuming no heat is lost, what is the final temperature after they reach equilibrium? So this is going to be your equation. So this is better taught in physics. Reason why we add this in. Direction matters. In order to flip direction, we have to change the sign. All you really need to know is this equation. Heat gained is equal to negative heat lost. So if you wanted to flip, so one is in the direction of leaving or being released. If you want to flip that to being gained, you just add a negative sign. Well, we know that heat gained or lost will be equal to the mass times change in temperature times Cp. So the water is going to gain some heat. So the mass of water times the change in temperature of water times the Cp of water will equal the mass, equal to negative the mass of lead times the change in temperature of lead times the Cp of lead. So the mass of the water is 500 grams. I'm going to take delta T and expand it. So delta T is equal to final temperature minus initial temperature. So the final temperature I'm going to call TF minus the initial temperature of water, 20 degrees Celsius, and the Cp of water is 4.184 joules per gram degree Celsius. And that will be equal to negative mass of the lead, 50 grams. Again, I'm going to take delta T and expand it. The final temperature of the lead minus the initial temperature of the lead, 200 degrees Celsius, times the Cp of lead. So the final temperature of the water is going to equal the final temperature of the lead once they reach equilibrium. This is just an algebra expression. All you have to do now is solve for TF, and that'll tell you your final temperature. By the way, what would y'all guess the final temperature would be? If we took 200 degrees Celsius cubed, let's say 50 grams, and drop it into water, what would y'all think the final temperature would be? The water started out at 20 degrees. What'd you say? No. So the heat gained by the water will be equal to the heat loss. So some of the heat is going to be transferred into it. So we have a cube that's at 200 degrees Celsius, 50 grams, and we have a 500 gram container of water that's at 20 degrees. When they mix, some of the heat is going to transfer into the water. So this is going to lose some heat, and this is going to gain some heat, right? So the water is going to, so if you drop that into some water, the water is going to heat up, and the cube is going to cool off, right? So it tells us that the amount of heat the water gains is going to be equal to the amount of heat that the cube lost. This negative sign comes into the fact that they're in opposite directions. Heat is being lost here while heat is being gained here, and heat lost is a negative. So how much? What temperature do you think water will heat up if you take it really hot? 110. Anyone got a different guess? So, do you know how to solve this algebraically? I would use the FOIL method. Do y'all know how to FOIL? So if you have A times B plus C, you distribute this in each one, so it'd be A times B plus A times C. We FOIL into it. So 500 times TF would be, I'm just going to drop the variables for right now. And then 500 would be minus, so 500 times 20, I'm too lazy to, 10,000. Now we FOIL this back in over here. So 500 TF times that. So that would be 2092 TF minus this times that. And we do the same thing over here. Negative 50 times TF, so we FOIL this over. It's just negative 50 TF. Negative 50 times negative 200 is a positive 10,000. Oh, and this is supposed to be, add another 0. That's supposed to be 10,000, okay. 20 times 500 is 10,000. And now we pull, so we multiply this to everything in the parentheses. Negative 50 times 0.128 is negative 6.4 TF. We multiply this over here and multiply that by this. Let me double check on that. Alright. Y'all done foiling, right? So again, when you multiplying something times something in parentheses, you multiply what's on outside to everything inside. So for example, if you have 2 times 3 plus 4, well, that's 7 times 2 is 14. Or you can FOIL it and have 2 times 3 plus 2 times 4. And then 2 times 3 is 6. 2 times 4 is 8. 8 plus 6 is 14. So this is the FOIL method. If you have something outside of parentheses, you just multiply it to everything on the inside. Now we have this expression. So now we want to group everything. We want to group final temperature. We want to group our variables on one side and our non-variables on the other. So I'm going to add 41,840 to both sides. That gives me 2092 TF. This minus this cancels out on that side. And now I'm going to do the same thing for TF. I'm going to add 6.4 TF to both sides. So 6.4 TF minus 6.4 TF is 0. So it cancels it out on the right side. And now we have a single term on the left. And so we can divide it on the right. So divide both sides by 2098.4. This divided by itself is 1. So it cancels out. And let me double check. That number seems slightly off. It is very easy to make a mistake. I was expecting this to be about a half a degree higher. Nope, that's correct. It only rose by half a degree. Yeah, which makes perfect sense to me. So remember this. Lead only takes 1/10 of a joule to increase its temperature. Water takes over 4 joules to increase its temperature by 1 degree. So again, water takes a lot of energy to do it. So 200 going down. So let me illustrate this. So to double check your answer. So let's look at what temperature lead goes to. So for lead is going from 200 degrees Celsius to 20 point, let's round it to, I'll put the whole thing. So how much heat did lead lose? Or how much, let me ask, what's the temperature change? So this is the final, this is the initial. So to double check your answer, just check to see if the energies on both sides match up. We get negative 179.451013 degrees Celsius. So the lead lost over 179 degrees Celsius of temperature, right? So the heat lost by the lead would be equal to its mass times change in temperature times Cp. Its mass is 50 grams. The change in temperature is negative 179.451013 degrees Celsius, and the specific heat is 0.128 joules per gram degree Celsius. So the amount of energy lead lost is negative 1,148.4864832 joules of energy. Right? So it went down by this temperature, and that's how much heat was lost by the lead. Let's look now at water. Water went from 20 degrees Celsius to 20.548 897 degrees Celsius. And this is its initial, this is its final temperature. So doing the same thing, the heat gained by the water would be equal to its mass. Its mass is 500 grams. Its change in temperature is 0.5489897 degrees Celsius. And the specific heat of liquid water is 4.184 joules per gram degree Celsius. So the amount of heat gained by the water is equal to 1,148.480.804 joules. Now, how many significant digits do we have here? We have at the most 4 here, 3 here. How many digits does these match up? These two values. They're equal to about 4 digits, right? These two numbers are actually, these numbers are accurate to 6 digits. So the heat gained by the water was 1,148.4808 joules, and equal to negative Q lost by lead, which negative 1,148.48648 joules. These numbers are about the same, right? So this confirms that my answer is correct. Again, it takes water a lot of energy to increase it. Lead doesn't take that much energy to make it change temperature. So lead loses over 179 degrees Celsius and there's also 10 times the amount of water, right? So there's 10 times the amount of water, and there's also, so let's see, the specific heat, so just comparing the specific heat, 4.184 divided by 0.128 is 32.6875. And then we also have 500 grams versus 50 grams. That's a factor of 10. And it's supposed to be 30. So 10 times 32, we would expect the temperature to change to be about 326 times greater for the iron. And let's compare the temperature The final temperatures changes was 179.45 versus 0.54899. We see the same value, 326.873. The same factor. So the temperature change for iron was 327 times more than the temperature change for water. That's because it has 10 times the mass, and the specific heat value is about 33 times greater. These two add up to expect to see a over 300 times difference in change. Again, the main thing is algebra. Boiling it down, making sure you don't make a mistake in the process. It might be easier to have worked it out like this. So you can redo any multiplication. We could have done the 4.184 times 500 first. So you could rearrange this as 500 times 4.184 times TF minus 20 and work out these first. Which is 2092 times TF minus 20. Then you can FOIL this out, which would be 2092 times TF minus 2092 times 20, which is 10,000. And we get the same thing. But it's just multiplication. And it's basic algebra. Yes, it's a lot of math, a lot of steps, a lot of places where you can make a mistake. But we haven't even gotten to the full equations where we do phase changes. Note, I ignored all phase changes in this problem. What happens if you take liquid gallium and drop it on some ice? Liquid gallium will start to freeze while the ice starts to melt. And we have a phase change in between in two directions. Wait until you have to do it on a test in 50 minutes. I had to rework that first example like 3 times. Here's the code word for the day.